My name is Ernesto Delfino Aguirre and I am mechanical and aeronautical engineer. I'm not a scientific background that I could spoiling for my affirmation in this video. Besides, my diction is very awful, that's the reason that I use a voice synthesizer. First of all, I will say the following by the way of apology using Chesterton words. My writing is bad and my speaking is worse. It's dreadfully sad and I don't care of course. Let's begin with the video.
Almost 200 years of mistake. The Navier-Stokes equations are bad writing. Navier-Stokes equations has already 200 years of being writing and has no solutions. So complex is the problem, that mathematicians just only want know if possible has a set bounded by physical sense of amount of energy. That means, solutions has no more energy that are involved in the whole flow. The physics left to mathematicians this homeworks, because the original set lead to nowhere. Only computational methods offer solutions by numerical methods, and save inconsistencies of main formulation. In any book about fluids mechanics you find this equations. This is the most used Navier-Stokes set of equations, for viscous and incompressible flow. There are four variables namely U, V, W, and P, and for equation. Then, why it can't solved. Rewriting the system, make matricial products and dropping force terms. Note a tiny change, I wrote the divergence of velocity on the right hand side. The diagonal matrix at the left, has a 0 in its main diagonal. The pressure has no equation for time. This lead to an ill-conditioned system. Then, this system at left, has infinite solutions as consequence Frobenius theorem. As see it, rank of coefficient matrix it's different of enlarged matrix. The problem is here. Let's think about two system, whose solutions must be the same. This implies. Then we need a time derivative for P. There is not a time derivative for pressure, hasn't history for evolve. In CFD we construct some equations for solve this problem, otherwise in analytics form this can't be done. Big efforts were done, to solve this equations. The always explored ended in failure. Why? Years ago, I was study a problem about Euler equations, and I was compare 5 different methods for solve it at low Reynolds numbers. Its results were partially successful, but with great limitations. Why? Then I realized, all methods start at same point, at same set of equations. I thought, if these equations were wrong? Could Navier-Stokes equations, for incompressible flow were wrong? I started from 0 again. I took the very start. The conservation principles, in first place, conservation of mass. And there is, the very key of the problem. If ρ equal constant, the substantial derivative is 0. And then, as consequence, the divergence of velocity is 0. I saw the same equations hundreds of thousands of times, if not millions. Only I saw this in the whole world. Can you see it? Well, density it's not only a state variable, in fact is a dependent variable of others. Think in the gas perfect law, there are a relationship between the temperature, the pressure, and density. If we take the substantial derivative of the perfect gas law, we obtain an expression for the substantial derivative of ρ in two terms, pressure and temperature. Then, we could write if ρ were constant, the consequence, divergence of velocity is sustained. We proved that divergence of velocity field, it's a consequence of incompressibility, not a statement, not a hypothesis. It's a slight difference but fundamental. Then, we could write conservation of mass in two forms. We need put in scene the energy equation, because we have another state variable, the temperature. For an incompressible fluid, the energy equation in terms of temperature is make some replacement. Put energy equation in the mass conservation equation, finally can obtain an equation in terms of pressure only. If you put in scene divergence of velocity equals 0, you could prove that energy and mass equations for perfect gas are the same for incompressible flow. Using the new relationship in Navier-Stokes set of equations, we write this matricial form. Then, this system satisfies Frobenius theorem, and therefore has one solution. We omitted terms about dissipation for clarification purposes. Writing now in equation form, we have two forms for this equations. 1. Take in account divergence of velocity, other without this term. Remember that divergence of velocity is 0, as consequence of density is constant. Finally, the mistake is ours. Because we haven't made a revision of this equations, using more deep and complete perspective with new knowledge that were posterior to published Navier-Stokes equations. Indeed, thermodynamics books and papers about gases' behavior, their laws, and relationships, were published a decade after Stokes' publication of his hypothesis and the derivation of that well-known Navier-Stokes equations. But, we must understand that the focuses were pointed to solve fluids like water, and others like vapor and gases' behavior were studied in thermodynamics fashion. We could say that the solutions of Navier-Stokes equations depends of a state equation for fluid. An equation that relation density and others variables of the problem like pressure, temperature, and velocity. And using chain rule for derivatives. We construct a set of equation that avoid the intermination and make possible obtain a solution for that fluid. In other words, we have a system suitable for each kind of fluids. I think now, we must encourage to use the set equations and open new ways in the study and analysis in fluid mechanics. When we talk about millennium problems, Dr. Charles Pfefferman described in his paper Existence and Smoothness of the Navier-Stokes equation the basis for demonstration of existence and smoothness of the solution, for the Clay Institute. These demonstrations could be one of this. Existence and smoothness in R3 or Z3, breakdown in R3 or Z3. Take the first alternative. A synthesis presented in mentioned paper puts clearly the conditions to satisfies the solutions in the mathematical sense, but state without a doubt that the solutions has to be physically reasonable and be bounded by the energy criteria. Has to be physical sense. When you try to prove mathematically, you face a big trouble with this term. It's not bounded. But, if you use this new set of equations with time derivative of pressure, this inequality become in this. That it be clearly bounded in physical sense. Thank for watching. I hope you enjoy a newer point of view that I think is correct, and if you want contact me, my email is in the descriptions.